If we have two planar networks, there's a natural way to glue them together, just like we glued together elements of the temporally Lieb algebra. And if we do that, then their path matrices turn out to be, I guess, what you would expect. We multiply them. So let's let planar networks G and H of order n have path matrices A and B, respectively. Then the concatenation G glued to H has path matrix AB. I'm going to write SIG for the ith source of G SIH for the ith source of H, etc. Now let's let C be the path matrix of G concatenated with H. You'll observe that the weighted sum of paths from source I of G to sinc J of H, well, let's say source I of G concatenated with H, which is the old source I of G, to Tj of G concatenated with H, which is the old sinc J of just H. This can be decomposed as a sum of weights of paths passing through. So we start on the left side of G, and to get to the right side of H, we have to sort of cross the bridge to go from G to H. So they'll have to pass through either sinc 1 of G, which is the same as source 1 of H, because that's where we glue them together, or sinc 2 of G, which is the same as source 2 of H, because that's where we glue them together, etc. We draw a picture. So let's say these are the sinks of G, and these are sources of H. So this part is G, and this part is H. We have all these edges. So if we're going to go from source I over here, we somehow go through the planar network, and then we have to choose one of the bridges to go across where we leave G and enter H. It could either be the first one, the second one, third one, etc. up to the nth one. And then we eventually get to the sync J of the new planar network. So that means that the sum of weights is, we'll sum over the bridges. So k equals 1 to n. So we'll have the sum of weights of edges from Si to Si of G to Tk of G, which is the same as Sk of H, and then we have to get from there to the sync that we're going to. So then we have sum of weights from Sk of H to Tj of H. Going from Si to Tj, Si on the left to Tj on the right. But this is a sum as k goes from 1 to n of Aik Bkj, which we know is the ij entry of the matrix AB. And it turns out that the minors of the product matrix AB have a nice expression in terms of minors of A and minors of B. That's called the Cauchy-Binet identity. It says that, I'll write this in delta notation, the ij minor of AB equals a sum over all subsets K. Now, of course, I and J have to be the same, or we wouldn't have a square matrix to take the determinant of. So a sum over all subsets K such that K has the right number of elements in it. We have the Ik minor of A times the Kj minor of B. So this formula looks a lot like the entry formula. In fact, this is a special case because the ij entry of AB is a 1-by-1 submatrix, so it's a 1-by-1 minor. This generalizes to other sizes of minors. So we've got the product of minor of A times minor of B, and these indices on the inside have to match, the capital K's have to match, and then the indices on the outside, little I and little j in this case, or capital I and capital J in this case, have to match what we're looking at in the product. And I'm going to leave this proof for you for homework. The end.